Hi, in today's video, I'll be going through functions. So, you already went through maybe basic courses in calculus or linear algebra or other mathematics in your high school or previous days. And so you already dealt with functions many times. And so you already know what is a function technically. So many courses will just give you the informal definition where a function from the set x to the set y is just a correspondence or assignment or a rule that assigns each element in this x to a unique element in y. Assigning every element in x means that it is everywhere defined, and to a unique element in y just means that it is well defined. And so a function needs to be both well defined and everywhere defined. But you can see I put quotations on the correspondence because then you can just ask what is a correspondence. But we like to know is an assignment, basically the idea. And so we can just write our notations like this. X is the domain and y is called the codomain. So the letter x is sent to the letter y, which equals to fx. An example will be like this. x1 is sent to y1, x2 is sent to y1, x3 is sent to y4. You can see not everything in the target needs to be hit, but everything in the source, x, the domain, needs to have an element in the target. And so it's just an assignment. You can just assign it, but it can only be assigned to one other element. That's the uniqueness part. Other examples that we've already seen in courses like calculus is x being assigned to sine x. So the graph will just be as follows. Then, but what is this graph that everyone is talking about? Well, you can see that in the first example, you can just, if you want to know this correspondence, you can actually just write nicely in ordered pairs and then you just put a set. And so this is known as the graph. It is the subset of all ordered pairs of x cross y such that y is fx. So it's a subset of x cross y. So if you just take the sine x example, when we want to draw the graph, this is known as the graph, and it's actually just a subset of the whole plane xy. So you can see you already do a lot with functions in calculus and other mathematics courses that you went through. But now to rigorously understand what is this graph, it is just a subset of x cross y. And so when we want to give a function, we can just formally define it as an ordered triplet. Why we want to give this definition is because it allows us to say when two functions are the same and what gives a function. So you want to give a function, you just need to tell us the domain, the codomain, and the graph in this ordered triplet form. And this ordered triplet must have the property that every x in this set has a unique y in this set such that the ordered pair lies in the graph. And so by giving this definition, you say that two functions are equal if this is equal, and the graph is equal. And so this is what it means to have two functions are equal if their behaviors are equal from the same set to the other source set, the target set I mean. And so you can see that this corresponds well to our definition informally. So there's consistency, and that's why we like to give this formal definition. While some people don't like the idea of ordered triplets, but since we've already done videos on set theory, you can look through them to understand what are ordered pairs and you can generalize them to ordered triplets. By having a formal definition of function, there reduces any misconception and inconsistencies. Now that we know what a function is, we can say what is the range of a function. The range of a function will just be the subset of the codomain. So it's just known as the image of f also. So that means the elements in Y such that there exists an X such that Y is fx. Or you can say there exists an X such that X comma Y lies in G of F, the graph of F. And obviously it will be a subset of Y because you take the elements from Y. So some special functions to note is the identity function. This always exists as long as there's a set. So every set has its own identity function. And it's just sending all the elements in X to the same element X. And then there is the composition of functions that we like to take note of too. So let's say you have f from a to b and you have a function from c to g called g. Then the composite of f and g is just the function g circle f. This means you apply f first, then followed by g. And if you see it's from a to b, and b and c will be somewhat similar such that the range of f will lie inside the domain of g as well. And later we'll see why. But basically g circle f will be a function from a to d. So a is the domain of f and d is just the codomain of g, such that g circle f it sends x to the value g of fx. And so you can see fx must lie in the domain of g. And so the range of f must lie in the domain of g. So to draw a more simple diagram, you can just let b equals to c. So if b equals to c here, then the range of f you already know is a subset of b, which equals to c, means it's a subset of c, so it's defined. So a is this, b or c is this, d is this. So x is sent into this b whole domain b, and then g will just send the range f to a subset of d. You can then see that if range of f is not a subset of c, then g circle f is not going to be defined. Because it could be the case that f sends an element x to somewhere outside c and then the function g don't know what to do with it. So we don't define it. We also like to note that f circle g is not the same as g circle f in most cases. And this just means that the composition of functions is non-competitive. You can refer to page 236 to better understand it by seeing more examples. I'll let you do that on your own reading, but really please read if you do not understand it. Now that we know all these definitions and we already take note of the what are functions, let's prove something about functions. What we'll prove is the associativity of composition. So we have three functions, x to y, y to z, and z to w. We want to prove that h circle g, this function composed with f, is the same function as h composed with g circle f function. Well, you can firstly verify that the domain and codomain is the same. So what you want to do is just check that the graph is the same. And for the graph to be the same, you want the behavior to be the same basically. And this means for all the x in the domain, the function sends x to the same value. So we take our left hand side, h circle g's whole thing circle f, take in the function, the parameter x. Well, you evaluate the first one first, so it's fx. Then you take h circle g of this fx. And because this is h circle g, it just means h take in the parameter now gf of x. But then gf of x can be expanded out into g circle f. And this now can be expanded on h circle whole thing of g circle f. And that is the right hand side. And so your left hand side is the same as the right hand side output. And so, we say that the two functions are equal, and hence you have proven the associativity of composition. And so you can see how functions just act as a way to put in something and you get an output. Of course, functions in much abstract mathematics may not be as simple as this, but understanding functions at our level now will play an important role in understanding abstract mathematics higher on. And so you need to be very clear of the logic laws in functions and how to prove that two functions are equal. We'll move on to more properties about functions that we want to say in the next video, so stay tuned. Thank you.